everyone. So switching gears back to children, I'm really interested in understanding how the brain develops as children learn and master math skills. So before I get started, I have a question to ask you, the audience. Can you guys tell me the answer to this problem, and feel free to show me with your fingers. Fantastic. I'm glad you all know the answer to that. So typically, adults like you can retrieve this fact very quickly and efficiently from memory. This is because you weren't using any sort of calculations either in your head or counting on your fingers, I hope. Essentially, you just knew the answer. Children ages 7 to 9, however, are not able to retrieve these facts as quickly and as efficiently as adults. This is around the age when they're beginning to solidify their basic arithmetic skills, and during this time, children don't have the fact retrieval memory systems as strongly in place as adults do. So as we all know, the ability to retrieve arithmetic facts from memory is very important for children to develop because it's just such a critical component to being successful at school. And there's an extensive amount of individual and temporal variability during this development process. For example, if you have two children in the same classroom, there are some kids who are struggling with these concepts, and there are also other children who are doing very well. And also, there's a lot of temporal variability also in terms of when this trajectory to switching to using the memory-based approach occurs. Which leads us to ask the critical question, how does the ability to retrieve math facts develop in children, and what are the individual differences underlying this process? So children employ far less efficient strategies to solve basic arithmetic problems compared to adults. They use multiple sorts of counting strategies, which include starting from the smaller number, counting their way up to the answer, or starting from the larger number, counting their way up to the answer. They also use another strategy in which they break down a larger number into smaller numbers that are easier to compute to retrieve the answer. And then finally, they make this leap where they are solely retrieving facts from their memory. So in order to understand how the ability to retrieve math facts changes in children, it's really important to understand temporally how these strategies develop. So as we are all aware of the Longitudinal theory, which suggests that there are abrupt transitions or shifts in the problem-solving approach the child uses, it's very similar to a step-like progression. However, more recently, Siegler and Geary have suggested that learning advances are not really categorized by these broad and abrupt shifts, but more so by fluid distributions that essentially overlap with one another. And this is visually analogous to overlapping waves, as you can see over there. So looking at one specific age range right here, you can see that at one time point, children are using multiple strategies to solve problems, and this fact retrieval strategy is rapidly improving. However, we still don't know the neural representations of how these different strategies develop over time. So broadly speaking, many studies have consistently observed a set of widely distributed brain regions, namely the frontal, parietal, and temporal networks, which are implicated in arithmetic task processing. Specifically, the intraparietal sulcus, or IPS, angular gyrus, and dorsolateral prefrontal cortex, among others. In addition, these studies used a univariate approach, which we all know provides a stellar computation of overall magnitude of mean activation associated with arithmetic problem solving. However, it provides little insight into the distributed neural representations during problem solving. So running a multivariate representational similarity analysis provides a much clearer picture of the distributions of the neural representations during problem solving, and this is a tool that we will be using during our analysis today. So a little bit more on this. Okay. All right, so this tool is fantastic because it can functionally distinguish between two different arithmetic problem-solving strategies. And in our case today, we will be examining complex problems, shown in red, and simple problems, shown in white. So the complex problems, the operand range from 2 to 5, and the other digit ranges from 2 to 9. And simple problems are identical to complex problems, except one of the digits is always +1. And behavioral evidence has shown that simple problems are processed very differently from complex problems. Essentially, children process them more quickly, efficiently, and consistently. And they do this by using a specific type of counting strategy, which is called an incremental strategy, where they're essentially just thinking of the next number up. So the representational similarity analysis is first computed by using a GLM based on the model based on the response patterns for both the complex and simple conditions. So two separate maps which reflect neural activity are created by computing the difference between the complex problems subtracted from the baseline and simple problems subtracted from the baseline. We then use a searchlight method, which essentially searches over the whole brain at every voxel and every neighboring voxel within a 6-millimeter sphere to compute the correlation of neural activity between these two maps. So the final neural map reflects the representational similarity between these two types of problems. So a paper published from our group in 2011 used this analysis to compare the neural representations of complex and simple problems in typically developing children, shown in gray, and compared to children with developmental dyscalculia, shown in purple. And developmental dyscalculia is a mathematical learning disability which is very similar to dyslexia. So they found that these representations of these two different problem types, simple and complex, are in fact more distinct in typically developing children compared to children with developmental dyscalculia, specifically in the IPS. And since we don't know longitudinally whether these neural representations of complex versus simple problems become either more distinct or similar with development, this paper provides some evidence that these representations may in fact become more distinct. So circling back to our initial goals, we're interested in understanding how the dynamic brain changes that accompany the development of math skills. And more specifically, we're interested in what is that neural signature of the representational change that predicts individual gains in math learning longitudinally. So to answer this question, we will be using a longitudinal design paired with a math strategy assessment that I will be describing in the next slide. And we are doing this because we're interested in tracking the individual changes in brain function over time and how it relates to individual differences in strategy use. So, as I mentioned earlier, we will also be using a multivariate approach, the representational similarity analysis. And this tool is very critical to better understand and explore these distinct representations of strategies. So moving on to the experimental design, we had 30 typically developing children participate, 12 girls, and at time point 1, the children were between 7 and 9. So before the children went inside the scanner, they completed a strategy assessment task, which consists of they're sitting down at a computer with an assessor, and they see 18 single-digit arithmetic problems shown on the screen one by one. And after the child solved the problem, we classified what strategy method they used by using a combination of their verbal responses and the assessor's observation. So following this, the strategy assessment task, they completed the in-scanner task, which was an arithmetic verification task. Which consisted of the two conditions, complex and simple. And that was presented in a block format to gain sensitivity between the two conditions. So over 1 year later, the same children came back and they were between the ages of 9 and 11 at this time point, and we performed the strategy assessment as well as the in-scanner task using a different set of problems. So looking at the behavioral data at time 1, which is on the x-axis, children performed significantly better in these simple problems, which are labeled as the gray bar right here, compared to complex problems labeled in black. We then brought them back at time 2, and although there weren't any significant gains at time 2 compared to time 1, we believe those initial differences went away because they were reaching ceiling effects. So looking at the RT side, children were significantly faster when solving simple addition problems compared to complex problems. Both problem types improved significantly, and there was no interaction effect. So essentially, simple stayed faster than complex. Looking at the strategy assessment portion of the experiment, which I mentioned earlier was the outside of scanner task, where they verbally indicated which method they used to solve a problem, we observed only a marginally significant increase in retrieval strategy use, which is shown in green. However, we did see substantial individual differences in strategy use. Essentially, some people improved a lot, some did stay the same, and others didn't improve. So moving on to the imaging results, since we're interested in longitudinal changes, we computed the change in pattern similarity at time 1 and time 2, which is shown on the x-axis, and we measured the change in pattern similarity between these complex and simple conditions, which is shown on the y-axis. So our analysis revealed that the brain activation patterns in the prefrontal and parietal cortices become less similar at time 2 compared to time 1 when solving complex versus simple problems. Although we didn't find the IPS, we found other regions implicated in math cognition, specifically the superior parietal lobe, superior frontal gyrus, and angular gyrus. So this suggests that the neural representations of these two types of problems become more distinct with development. And as I mentioned earlier, several studies in this field have identified a set of widely distributed set of prefrontal and parietal regions involved in arithmetic task processing. So it's especially interesting to see these same networks at play here. So next we were interested in studying the behavioral metric of change. Specifically, we were interested in whether the individual differences in arithmetic problem solving could predict neural pattern stability. We computed a linear regression using the T-maps from our similarity analysis, and since children significantly improved from time 1 to time 2, we used RT as our covariate of interest. So the x-axes are RT scores that are d-transformed at time 2 subtracted from time 1, and essentially a positive value over here indicates a maximum improvement in RT, and a negative value indicates minimum improvement in RT. So longitudinal changes in neural pattern similarity in the following regions were negatively correlated with individual gains in RT when solving addition problems. So essentially, individuals who improved the most showed the least change in neural pattern stability, or in other words, one can interpret this as more distinct neural pattern representations. So after computing our RT correlation, we then computed a correlation between accuracy and the similarity maps. However, we didn't find any significant regions, but this was expected because children didn't significantly improve in accuracy from time 1 to time 2. So next we were interested in understanding how counting and retrieval strategies were functionally represented. So we computed a similar correlation using the data from our our strategy assessment, which was that outside of scanner task where they were asked to verify or asked to say what strategy they specifically used, either counting or retrieval. So specifically, we're interested in whether there were any significant similarities in the change in neural pattern stability for individuals who reported using a retrieval strategy, which is otherwise considered the more efficient memory-based strategy, compared to the changes in neural pattern stability, which were previously correlated with changes in RT. So retrieval strategy use was shown on the x-axis, calculated as the number of times the retrieval strategy was used. Okay, I hope third time's a charm. This doesn't happen again. Okay. Correlated with individual gains. So as you can see, longitudinal changes in I was explaining the retrieval strategy change on the x-axis, which was negative values essentially mean improvement, and the retrieval strategy was all the number of times they correctly used and answered the problem in conjunction with saying it was a retrieval strategy. So as you can see, the longitudinal changes in neural patterns similarity on the x-axis in the following regions were negatively correlated with individual gains in the retrieval strategy change when solving addition problems. So just like our previous RT correlation results, individuals who showed the most improvement in correct retrieval strategies showed the least change in neural pattern stability, or one can also interpret that as more distinct neural pattern representations. So I think one big takeaway here is that if your behavioral distinctness improves, your neural distinctness improves. And I'd also like to highlight the ventromedial prefrontal cortex, the inferior frontal gyrus, and the supramarginal gyrus, because it's really interesting to see this frontal temporal network at play here as well. And in fact, we do see some overlapping regions from the previous RT correlation, which include the supramarginal gyrus. So in aggregate, children become significantly faster at time 2 compared to time 1. And individual differences observed when using this retrieval strategy, there were individual differences that were observed when using the retrieval strategy approach to solve problems at both time points. So the representational similarity analysis revealed that brain activation patterns in the prefrontal and parietal cortices become less similar in each area from time 1 to time 2 when solving these complex versus simple problems. So this suggests that the neural representations of these two types of problems do in fact become more distinct with development. And finally, longitudinal changes in neural pattern similarity in the frontal, parietal, and temporal lobes were negatively correlated with individual gains in RT and the retrieval strategy used, which is the outside of scanner task when solving addition problems. So this may suggest that longitudinal changes in neural pattern similarity may predict individual gains in arithmetic problem-solving skills. And I think these findings are really interesting because it seems like this temporal trajectory of arithmetic problem-solving seems to be a very streamlined and distinct process. And we're currently following up with a few additional analyses which include looking at efficiency, or specifically the speed-accuracy trade-off of accuracy in RT, to see if that might give us some extra validation as to the neural networks at play here. And again, our end goal is to better understand how these processes work in hopes that one day we'll have less children who find math daunting and difficult and more children who enjoy the subject.